So there's a lot of theory behind the definite integral, but the thing is that this notation is what we're going to call the definite integral. And that notation of the definite integral is where you have the only difference is that you have these bounds a and b. And what the definite integral is going to tell us is it's eventually going to tell us the exact area under the curve, assuming that the function is greater than or equal to 0. So what it says is that if you have a function that is on or above the x-axis, so let's say I have like a little curve here, and if I integrate from a to b, computing this definite integral, this quantity definite integral from a to b of f of x dx, that is going to tell me the exact area under the curve. There is no approximation there. It is an exact answer. And to get that exact answer, it actually comes from the limit of the Riemann sums. If you take the Riemann sums as you go out to infinity. Now, in this course, we skip over the Riemann sum. If you were in a Calc 1 with analytic geometry, you would talk more about that. But what I do want you to know is that there is some theory that we're kind of skipping over, but at the end of the day, the definite integral, this quantity, the definite integral, represents the exact area under the curve if the function is on or above the x-axis. Now, the other thing I want to do is just take a minute, a pause here, and remind you that when there are no bounds, that's what we did in the last section, that is known as an indefinite integral. And when you are talking about an indefinite integral, that is when you add the plus c. So what would happen here is you would say that this is capital F, so some function, and then plus c. And when you're thinking about like the practical use of this indefinite integral, this would be used if you're given a derivative and then you want to find the original function. Now, that was in the last section where we talked about you would integrate, and then that would be used if you were given a derivative and wanted to go back and find the function. Now, in this section, we're going to have the same notation, but one difference. We're going to have these bounds from a to b. And when we have those bounds, that changes the meaning of this quantity. It now becomes a definite integral. So when there are bounds, then it becomes a definite integral. And if you think about like saying something is definite, it's not going to be a function that varies for any x. A definite integral is going to just equal a single number. So we're not going to get a function here, we're going to get a single number. And the use for this definite integral is it would give you the exact area if the function is on or above the x-axis. It also gives you what we call the net area if the function has negative values, but we're going to just, for this course, we just assume that it's for exact area, and we always assume that the function is greater than or equal to 0. So that's our key concept here, is that we're now switching gears. We're talking about when we have bounds. This is the definite integral, and that's going to give us a single number. And if the function is on or above the x-axis, that will represent the exact area under the curve.